Hello, and thank you for joining me for this Global Cement Optimisation conference session. In this session, we're going to look at a technology for optimizing one of the most common and energy-intensive process steps in the cement and bulk materials value chain, and that's drying. We'll start with a review of the current drying methodologies and why they require the energy they do, and then look at a new method of drying bulk materials that operates on a different principle. Many of the materials used in the cement and concrete supply chain have had to be dried before they were used. Either they were wet when they were sourced, or they have had to be washed, or they were exposed to the elements at some point. So drying is universal, and dryers sit alongside pumps, motors, and so on as a staple of the industrial world. However, drying is energy hungry, and it is so because of the thermodynamic principle that is used in almost all drying systems. That principle is thermal drying. Essentially, we boil off the water that we want to remove from our materials. That approach has a certain minimum energy requirement determined by the laws of physics. Within that frame, optimization means removing inefficiencies, but it can't go below the floor dictated by the physics of the method. Drying is a mature industry, and over the years, a wide range of approaches have been developed to deal with the specific demands of various drying requirements. The rotary drum dryer, or variations on the basic design, such as adding some kind of paddle or mechanical agitation to break down the material, is probably the most common type of dryer in the cement sector. After rotary drums, fluidized beds are probably the second most common systems in the field. And these are good systems. They're proven and reliable, and if they're specified correctly, should work well. But they are all thermal dryers, and they're grounded in the same basic physics. That physics works like this. You heat up the water you want to remove to its boiling point. Obviously, you heat up the carrying material too. When you get to boiling point, you then heat the water through its latent heat of vaporization. To give you an idea of the significance of this, if you heated your water from 20 degrees C to boiling, it will take around 7 times the energy that you needed to reach the boiling temperature to then turn the liquid water that is already at 100 centigrade into a gas at 100 centigrade. The latent heat of vaporization is an energy-intensive transition. In practice, that means that it often takes of the order of 200 kilowatt hours per ton of energy to dry common bulk materials. The wetter the material is, the more energy it's going to take to dry it, just because of this physics. Generally speaking, the finer the particle size of a material, the more moisture it tends to hold because of the greater surface area per unit of mass. So within the thermal drying paradigm, there is definitely optimization work to do, but it tends to be of the care and maintenance variety. You must continually make sure that the internal surfaces of your dryer do not become caked in an insulating rind or crust of material. This will act like limescale in a kettle as a drag on the system, slowing throughput and increasing energy demand. You need to regularly check that you do not have faulty steam traps or other heat loss faults that can cause the system to bleed away heat energy, often undetected. But these efforts can only get you to the theoretical minimum, and that minimum is still high. To optimize beyond that point, you need to find an entirely different system. Somewhat like the move from incandescent light bulbs to LEDs, you'll need to set aside the old architecture and make an outright jump to something that is based on a different premise and does not share the intrinsic constraints of the older technology. Coomtech's kinetic drying technology is just such a paradigm shift. The operating principle is to remove the water mechanically rather than thermally, to wipe it away. Now obviously, you can't use a windscreen wiper made of rubber to wipe moisture off a particle stream, but you can use high-velocity air to achieve the same thing. The kinetic dryer uses air knives to shear the water off the surface of the particles, in much the same way as a Dyson hand dryer drives the water from your wet hands. To dry material in this way, We feed the wet material stream into an airflow, dispersing the particles into a dilute phase pneumatic conveying airstream. The particles travel suspended in the airflow, and as they move along the pipe, they meet a series of air knives, which apply a high-speed, turbulent airflow to the surface of the particles. This separates the water from the material. The final stage is to separate the dry particles from the moisture-carrying air in a cyclone or a filter and baghouse. This slide explains why the particles stay dry after the air knives have sheared the moisture off them. After the air knives, you now have a dry material traveling in an airstream that has an increased water vapor content. What you need to avoid here is recondensation of that moisture back onto the particles. To prevent that from happening, the air is maintained above its dew point. That is, the air is kept just warm enough that its carrying capacity for water vapor exceeds the amount of water we want it to hold. As you can see in this graph, the water carrying capacity of air increases exponentially with temperature, but by 80 to 90 degrees centigrade, it is more than enough for our purposes. And whilst this does entail some heat, it is much, much less than would be required for boiling the water away. The energy cost of pumping and heating the air, which is, apart from some minor ancillaries, the sum of the energy demand of the kinetic dryer, is typically about a quarter of that required for thermal drying. So this slide shows you a schematic of the kinetic dryer. Running from left to right, you can see that material is fed via an auger into a hopper, and from there dropped through a rotary valve into the main drying line. This line is in effect a pneumatic conveying pipe. Material is carried at high speed in a dilute phase through this pipe and passes through one or more drying cartridges. These are banks of air knives, as discussed earlier, where the material meets a high velocity counter-directional air jet. This shears the moisture off the surface of the particles. This diagram shows 3 drying cartridges in series, but depending on the material being dried, you may need only 1 or 2. Finally, after the drying cartridges, the now dry material is separated from the moist air in a cyclone or a filter and baghouse. This slide shows you the kinetic dryer in the metal. This is our demonstration plant in Atkinson in the northwest of England. You can see towards the back of the building the feed auger conveying material into the hopper, beneath which sits a rotary valve. The main drying line is running from the background towards the foreground in this picture, and the drying cartridges are the labelled sections on the line. The one marked Treatment 3 that you can see in the foreground being the final stage before material goes to a cyclone. This is a CAD rendition of the plant and shows the approximate footprint of a module that will dry up to around 9 tons per hour, depending on the material, moisture content, and so on. The grey shadows you see here represent in outline the dimensions of standard 40-foot shipping containers. So this plant fits within the footprint of 2 shipping containers laid end to end. The height at its maximum is again that of 2 shipping containers. Obviously, your cyclones and storage facilities will be whatever you configure them to be for your particular plant. This is a closer look at the drying cartridges. The transport air runs down the center of the cartridge, and air enters at high speeds through tangential ports around the circumference of the transport pipe. 4 or 6 of these lines are fitted within a standard shipping container format frame, depending on the capacity required. This shows our first commercial unit in build in the UK. Running from left to right, you can see the blower unit, an end view of a drying cartridge, the assembly of the drying section into its mounting frame, and a cyclone on the right-hand side. This slide shows the completed unit loaded onto a truck ready for shipping. This unit was shipped to Australia, where it is now in commissioning as part of a lignite to hydrogen project in Latrobe Valley, Victoria State. So that takes you through the operating principle and configuration of the system and explains why it yields the energy savings that it does. Fundamentally, it's this. It takes less energy to blow water off than to boil it off. Now, I am going to say here that, as I noted earlier on in this talk, drying is a highly segmented sector with many different sectors for correspondingly different needs. There is not, and isn't likely to be, one drying technology to rule them all. and the kinetic dryer is likewise well suited to some situations and less so to others. Firstly, you have to be able to pneumatically convey the material. This means a particle size limit of approximately 5 millimeters and a reasonably free-flowing character. It's ideal for sand, fly ash, GBFS. It's no use for gravel, too big, and anything that's very sticky just isn't going to disperse enough in the air to be dried. Secondly, the water you want to remove has to be on the surface, because we have to be able to get at it with the air knives. If the water is down inside fissures in the material, this system will not easily remove it. But if your material does meet those criteria, then you have the potential to optimize a key step in your process down to energy levels never previously obtainable. This brings obvious commercial benefits. Energy is expensive, supply is volatile, regulations are tightening. These factors vary place by place, and they're much less onerous in some places than others, but everywhere the trends are towards greater cost and greater difficulty. If you can step across to a lower consumption system, you will have lower operating costs, greater independence, and in the end, greater pricing power in your market. We'd like to invite you to come and see this for yourself. We regularly trial customers and materials for them to see how their own material will run in the kinetic dryer, and we always encourage them to visit when we run their trial. After the trial, our engineers prepare a full report on the running conditions and the results of the trial. So if you have a material drying requirement that you are interested in moving to a lower energy methodology, please do get in touch. We'd be happy to help you. My contact details and those of my colleague Philip Jarvis are on this final slide here. Thank you for listening, and I hope this has been a helpful insight into energy optimization of the drying process.